Unless we discover problems after mission data review, SpaceX will attempt to catch the ship with the tower on next flight. Not long after Starship's upper stage touched down in the ocean, Elon Musk surprised everyone by announcing that SpaceX will attempt its first ever Starship catch on Flight 14. But is the vehicle actually ready for that? What makes catching the upper stage so much more difficult than catching the booster that SpaceX needs 13 test flights before even considering it? Well, let's answer all of those questions. Catching a giant ship coming back from space is hard, but hitting that subscribe button is surprisingly easy, and it could also let you know when a cool thing in the spaceflight world happens, so don't be shy about hitting it. Now let's get back to catching Starship. Okay, to begin, how hard would it be to catch the Starship upper stage? I mean, SpaceX has already caught the Super Heavy booster multiple times, so catching a shorter upper stage should not be that difficult, right? Well, not exactly. In fact, even though Starship is shorter than the booster, most engineers would probably tell you it's actually the harder vehicle to catch, and there are a few reasons why. First, let's talk about the catch points themselves. The booster was basically built around this idea. It has large, extremely robust hardpoints near the grid fin section that are specifically designed to take the enormous loads from the tower's chopsticks. On newer boosters, the grid fins themselves even double as part of the catch structure. Starship is a completely different story. Instead, it uses dedicated catch pins. Early versions carried test pins mainly to collect data, but an operational catch means those pins have to support the weight of the entire vehicle while it's being grabbed by the tower. And unlike the booster, those pins also have to survive one small inconvenience: coming back from orbit. That's because Starship doesn't just fall from a few hundred kilometers up. It slams into Earth's atmosphere at nearly 7.8 kilometers per second. The booster, by comparison, is only traveling around a couple of kilometers per second before it begins its return. It still moves incredibly fast, but it's nowhere near orbital velocity. That difference is absolutely massive. Even after atmospheric drag does most of the braking, Starship has to get rid of far more energy before it can even think about lining up with the tower. Depending on the exact masses, you're talking about roughly 10 to 20 times more kinetic energy than the booster has to deal with during recovery. That's like comparing dropping your phone onto the couch versus throwing it out of a moving car. They're both technically impacts, but one of them is going to ruin your day. And that leads to another challenge. The booster's catch happens after a relatively short trip. Starship's catch comes after an orbital mission, a deorbit burn, one of the hottest atmospheric reentries ever attempted by a reusable spacecraft, the belly flop maneuver, the landing flip, and finally a powered descent toward the tower. That's a lot of opportunities for something to go wrong. If the heat shield loses too many tiles, the wrong parts of the vehicle could overheat. If the attitude control is even slightly off during reentry, the landing solution changes. If the timing is off by just a little, the tower isn't grabbing anything except empty air. And unlike the booster, Starship also has another big requirement. Its Raptor engines have to relight reliably after spending a long time in space. Rockets aren't cars. You can't just leave them parked for an hour and expect them to start every single time without complaining. Everything inside the tanks is sloshing around. The propellants are changing temperature, pressures are shifting, and then, at the most critical moment of the entire mission, you ask the engines to fire perfectly. Starship also behaves differently because its mass distribution and center of gravity aren't the same as the boosters. Even if it's lighter at the catch, it responds differently to steering inputs, which means the guidance system has to solve a different problem during those final seconds. So when you put everything together, an upper stage catch isn't just a booster catch, but higher. It combines orbital reentry, extreme heating, long-duration spacecraft operations, engine relights, an incredibly precise landing, and a successful tower catch, all in one mission. Pulling that off would be one of the biggest milestones SpaceX has ever achieved on the road to full reusability. So, with all that, is Starship actually ready to be caught? Honestly, after Flight 13, it might be. The mission gave SpaceX a lot of confidence. Ship 40 reached orbit, survived re-entry, pulled off the landing flip, and then made a nice, soft landing in the ocean. That's basically the entire catch sequence, right up until the very last moment. Because the biggest difference between splashing into the ocean and getting caught by the tower is, well, what you're aiming at. Instead of targeting a giant body of water that's, let's be honest, pretty hard to miss, the ship has to fly itself into a very precise position next to the launch tower so the chopsticks can grab it. It's kind of like switching from parking in an empty parking lot to backing into the only open spot downtown during rush hour. The important part is that Flight 13 showed the guidance and navigation systems were incredibly accurate. The ship flew exactly where it was supposed to, all the way through landing. So from a flight control perspective, SpaceX has pretty much demonstrated everything they can without actually going for the catch. And it's not just the flight results giving them confidence. Starship version 3 also comes with a few hardware upgrades that really make this kind of mission a lot more practical. For example, the aft flaps now use a single actuator with 3 motors instead of 2 separate actuators. That gives the system more redundancy while also making it lighter and less complicated. It's one of those rare engineering changes where everyone somehow wins. Version 3 also has a much better reaction control system, upgraded valves, full vacuum insulation around the header feed system, a new electrically driven cryogenic recirculation system, and a dedicated setup for managing propellants around the engines during long coasts in space. That last part is especially important because a return to launch site mission is a completely different beast from the suborbital flights we've seen before. The ship spends much longer in orbit, follows a different trajectory, and then has to come all the way back to Starbase with everything still working perfectly. That's asking a lot more from the vehicle. But of course, catching Starship isn't just about the ship. You also need something that's actually going to catch it. And right now, that's Pad 2. It is currently the main and only launch pad that's been set up for catching the upper stage. The chopsticks are now shorter than the old pad, which lets them move faster and track the vehicle more precisely during catch operations. Their main actuators have also been switched from hydraulic to electromechanical systems, improving speed while adding more redundancy and reliability. Because Flight 13 went so well, a lot of people are already looking ahead to Flight 14. And honestly, the optimism makes sense. If post-flight inspections don't uncover anything major, there's a good chance the next launch could happen just a few weeks later. Really, there are only a few things that could slow SpaceX down. The first would be damage to the launch pad, or Stage 0. But so far, there hasn't been any sign of that. The pads seem to handle Flight 13 surprisingly well. The second would be if engineers find a serious issue while going through all the flight data and inspecting the hardware. Just because a mission looks smooth on the live stream doesn't mean the engineers aren't going to spend weeks looking for tiny problems. Rockets are kind of like your laptop after an update. It might seem fine at first, and then 3 days later you discover something weird that nobody noticed. And then there's the FAA. Normally, any major anomaly could trigger a formal mishap investigation, which would delay the next flight. But fortunately, that doesn't seem to be the case here. Flight 13 did have a couple of off-nominal moments, including an early engine shutdown during the boostback burn and a harder-than-planned booster splashdown. But according to reports, after reviewing the telemetry and flight data, the FAA determined there was no public injury, no property damage, and the events didn't meet the threshold for opening a formal mishap investigation. So that's definitely good news for Flight 14's timeline. Here's the question everyone's asking. Will Flight 14 finally catch both stages? Eventually, that's the goal. SpaceX wants both Super Heavy and Starship returning to the launch tower after every mission. Now the ship, I can actually see that happening. The booster, I'm not quite convinced yet. Flight 13 showed a lot of progress. The boostback burn worked, the descent looked solid, and the landing burn started right on schedule. But then, one of the Raptor engines failed to restart. The booster still made it down, but it hit the water harder than planned. That's a pretty clear sign that version 3 Super Heavy still hasn't fully proven its final landing sequence. So if I had to guess, Flight 14 will probably have the booster splash down again instead of risking a tower catch. Fix the engine restart issue first, then go for the catch later. That seems like the more SpaceX-like approach. Push the limits, just not all of them at once. And honestly, that might work out perfectly anyway. SpaceX has one active launch pad in Texas and a second Starship pad undergoing renovations there. 2 Starship launch sites are under construction at Kennedy Space Center and Cape Canaveral Space Force Station in Florida. So right now, SpaceX effectively has only one operational catch tower. Even if the booster was ready, there's still a practical question nobody outside the company really knows the answer to. Can the ship stay in orbit long enough for ground crews to secure the booster, clear the pad, and get everything ready for a second catch? Or will SpaceX need 2 fully operational towers before they can routinely catch both vehicles on the same mission? For now, we simply don't know. What we do know is that Flight 14 has the potential to be one of the most exciting Starship flights yet. Whether it's a ship catch, another booster recovery, or maybe both someday, the next launch is going to be one heck of a show. And honestly, I can't wait to watch it. If you're just as excited as I am, let me know by dropping "Let's catch that ship" down in the comments. Before we wrap up, there's one more thing that's worth talking about. And honestly, I think it's one of the most interesting discussions happening right now. After Flight 13, you can really see the conversation starting to change. A few months ago, everyone was asking, can SpaceX even catch Starship? Now the question is becoming, okay, how do they make this practical? Because catching one ship is cool. Catching hundreds of them every year is a completely different challenge. One idea that's been getting a lot of attention is building dedicated landing towers for Starship. The concept is pretty straightforward. Launch Pad 1 and Pad 2 would continue doing what they're designed for, launching rockets, while returning Starships would fly to separate towers built specifically for catching them. These towers wouldn't need launch mounts, fueling systems, or any of the complex infrastructure required to send a rocket into space. Their only job would be to catch returning vehicles. There are some obvious advantages to that approach. Your launch towers stay available instead of being occupied by a vehicle that just landed. Returning ships don't interfere with launch operations. And if flight rates continue increasing, SpaceX could simply add more landing towers without having to build entire launch pads. These landing-only towers would be much cheaper since they wouldn't need all the plumbing, propellant systems, and ground equipment that make a launch tower so expensive. It's a pretty sensible idea, but it doesn't really match Elon's long-term vision. Both Elon Musk and Gwynne Shotwell have repeatedly said that the ultimate goal is to relaunch a Starship roughly 1 hour after it lands. That's a completely different level of reusability. Instead of catching the vehicle, moving it somewhere else for inspection, and preparing it for another mission days later, the idea is to catch it, refill the propellant tanks, load a new payload, and send it back into space almost immediately. In other words, they want Starship to operate much more like an airliner than a traditional rocket. Of course, getting there is going to be incredibly difficult. For starters, the propellant system alone creates a long checklist after every landing. Methane naturally boils off over time, the oxygen system has to be purged, moisture can build up inside the tanks, and engineers still need to verify that everything is functioning correctly before refueling begins. None of those tasks are impossible, but together they take time. Then there's what is probably the biggest engineering question of all, the heat shield. Flight 13 looked fantastic from the outside, and version 3 clearly handled re-entry much better than previous vehicles. But one successful flight doesn't prove the system is ready for rapid reuse. Engineers will still want to inspect the tiles carefully to see whether any cracked during re-entry, whether the adhesive degraded under extreme temperatures, whether thermal cycling loosened anything, or whether hidden damage developed beneath the surface. Those are exactly the kinds of problems that only show up after careful inspections. History also gives SpaceX plenty of reasons to be cautious. The space shuttle relied on thermal protection tiles that demanded enormous amounts of inspection and maintenance after almost every mission, which became one of the biggest reasons turnaround times were measured in months rather than days. Even if SpaceX eventually manages to prepare the vehicle for another launch in just 1 hour, Starship usually can't return to Starbase 1 hour after liftoff in the first place. Once it's in orbit, the Earth keeps rotating underneath it, so the spacecraft often has to complete several more orbits before its ground track lines up with Starbase again. Depending on the mission, that could mean waiting 3 or 4 orbits before beginning the deorbit burn. So the timeline is really more like this: launch, spend several hours in orbit, return to Starbase, get caught by the tower, spend about an hour preparing the vehicle, and then launch again. That's an important distinction because when Elon talks about a 1-hour turnaround, he's talking about 1 hour after landing, not 1 hour after launch. Even so, if SpaceX can eventually make that a reality, it would completely change how we think about rockets. At that point, Starship wouldn't just be reusable, It would be operating in a way that's much closer to commercial aviation than anything the space industry has ever achieved.